Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to talk on module Energy Dispersive Analysis of X-rays, that is EDAX, under the paper Characterization of Materials 1. So students, let us see what we are going to learn in this module. In this module, the basic analysis principles of EDS will be studied. Secondly, the principle of characteristic X-rays generation will be discussed. Then, the methods of qualitative analysis of X-rays generated EDS spectrum will be discussed. Instrumentation of EDAX along with the description of components will be given. Quantitative analysis is also described along with non-conductive specimen analysis. Energy dispersive analysis of X-rays, also known as energy dispersive spectroscopy, and it can also be abbreviated as EDS, EDX, EDXS, or XEDS. Sometimes it is termed as energy dispersive X-ray microanalysis, that is EDXMA, or energy dispersive X-ray analysis, which is EDXA. It's an investigative method which is widely employed in elemental or chemical characterization of objects. The sample may be of any form, such as solid thin films, solid powder, liquid sample, or even a pellet. Let us study the basic principle of EDS. A typical setup of the EDAX is similar with that of SEM setup. More specifically, EDAX is actually inbuilt within the SEM setup. The working of EDX is based on electron focusing, same as in SEM. Electron beam excitation is employed in SEM and scanning transmission electron microscopes STM, whereas the X-ray beam excitation is present in X-ray fluorescence, that is XRF spectrometers. A detector converts X-rays into voltage signals, which feeds a pulse processor to measure the signals and pass them to data analyzer for display and investigation. The EDS semiconductor detector assembly is shown in the figure. The silicon or lithium detector, cooled at cryogenic temperatures by liquid nitrogen, is often employed. Additionally, some modern systems come with silicon drift detectors (SDD) employing Peltier cooling systems. To produce characteristic X-rays from an object, it is bombarded by either a highly energetic beam of charge carriers, that is, electrons or protons or X-rays. The atoms of the sample contain the ground state, that is, unexcited electrons in discrete energy levels, or electron shells bound to the nucleus. An electron from an inner shell may be excited by an incident beam, thereby removing it from its shell and generating a hole where electron was present before excitation. This hole can be occupied by an electron of a higher energy shell. The difference in energies of the higher and lower energy shells is emitted as an X-ray. Quantitative measurement of the energy and number of these X-rays can be done with energy dispersive analysis of X-rays. Since the energy of these X-rays is characteristic feature of energy difference between two shells and atomic structure of discharging element, EDAX can be employed to identify the elemental composition of an object. Some basic advantages of EDS includes the broad range of elements, that is, from boron to uranium, can be examined synchronously. Figure 2 shows a typical EDS spectrum. Here, the x-axis represents the X-rays energy and the y-axis depicts the X-ray counts. It is a valuable tool for qualitative as well as quantitative analysis. The above figure showing unique peak positions of various elements which corresponds to the feasible transitions in its principal energy level. Let us now study the characteristic X-rays generation. When a sample is irradiated with highly energetic beam of electrons, then a characteristic X-ray is generated. Due to irradiation, when an electron is excited from the inner shell of its parent atom, the vacant place is occupied by the higher energy electron from the outer shell, and the energy difference between the two shells is emitted as an X-ray. The joule of energy which is liberated in electron transfer is dependent upon from which shell it is transferring to which shell. The emitted X-rays energy as well as the number through specimen is obtainable by an energy dispersive spectrometer. These emitted X-rays are known as characteristic X-rays because their energies, that is wavelength, are specific to the element from which it is emitted. Thus, this technique can be used for elemental analysis. When K-shell electrons are excited, they emit characteristic X-rays which are termed as K-lines, and those emitted from L and M shells are called L-lines and M-lines respectively. When the element is heavy, then its characteristic X-ray energies are also higher. Therefore, incident electrons of higher energy are required. Different types of X-rays are emitted when incident electrons strike the atomic nucleus, and these are known as continuous X-rays, white X-rays, and background X-rays. Samples, qualitative compositional data can be known from the respective peak positions with appropriate energies. The X-ray quantum number measures the concentration of the elements, that is, the height of the peak, but there is no linear connection between quantum numbers and elemental concentration portions. The concentration calculation requires the net count rates, and characteristic X-ray energy of a specimen is the marker of the specimen atomic number. We next discuss the instrumentation of the EDX. Figure 4 shows the working arrangement of EDS with SEM. This instrument is mainly composed of four components. First is the electron beam source, second is the X-ray detector, third is the pulse processor, and the fourth is the analyzer. Let us describe the components briefly. First is the electron beam source, as EDS is employed with the scanning electron microscope. Therefore, the same electron gun which is used for field emission is used as the incident electron source, and to focus the beam, lenses are used along with aperture. The energy of the electron beam has to be carefully selected to overcome the compromise between the resolution requirements and the production efficiency of X-rays. The produced X-rays are detected by two crystal spectrometers. Second is the X-ray detector. The X-rays counts, which is the abundance of emitted X-rays versus X-rays energies, are measured by the EDS detector. Detector, a solid-state device which is based on lithium-drifted silicon. As X-rays strike the surface of the detector, a charge pulse is created. This charge pulse is directly proportional to the energy of the incident X-rays. Let us study the parts of detector. The first one is the collimator assembly. The purpose of the collimator is to provide restrictive aperture through which X-rays should pass in order to make a way to detector. The collimator ensures that only X-rays from the region being excited by the beam of electrons are detected. The next one is the electron trap. The background artifacts are created when electrons penetrate the detector. The purpose of the electron trap is to guarantee that only X-rays should enter the detector. It comprises a pair of permanent magnets to strongly deflect the passing electrons. The window. The purpose of the window is to provide isolation from the microscope chamber to maintain vacuum inside the detector. At the same time, it's being as transparent as possible for allowing glow energy X-rays. Charf comprises a thin window composed of polymer and transmits X-rays from elements which are heavier in comparison to beryllium. Next is the crystal. In detector, crystal material used is silicon drifted with lithium around 3 mm thickness for small levels of impurity compensation. When X-rays are incident on the crystal of detector, then its energy gets absorbed by a series of ionizations within the semiconductor to generate electron-hole pairs. The absorption of every 3.76 electron volt of X-ray radiation generates an electron-hole pair. Therefore, 1966 electrons are generated by a nickel K alpha X-ray photon that of energy 7471 electron volt. The electrons promoted to the conduction band can freely move in the crystal lattice. Every excited electron leaves behind a hole in the valence band which acts as a free charge carrier within the crystal. When the front and back face of the crystal are biased with high voltage, these electrons and holes are swept towards the opposite poles, thereby generating a charge signal whose size is proportional to the incident X-rays energy. The diagrammatic illustration of X-ray interaction with crystal is shown in figure 6. FET, the field effect transistor, performs first stage amplification, which measures the charge released within the crystal by the incident X-ray and converts it to a voltage output. FET is nowadays integrated with the chips in order to greatly enhance the resolution along with the throughput, which is achieved by reducing noise through minimizing the capacitance between FET and anode. During operation, charge is accumulated by each incident X-ray on the feedback capacitor, thereby producing sharp voltage steps. The step size of this voltage is proportional to the energy of the incident X-rays. Restoration of the build-up charge is required periodically to avoid pre-amplifier saturation. Figure 7 shows the graph representing the voltage step size. Let us discuss the cryostat. EDS detector is a self-enclosed vacuum system which is called the cryostat, having liquid nitrogen or a cryogenic pumping. The crystal and FET are mounted on cooled finger within the cryostat to reduce noise by cooling. The cooling is necessary as the detector produces small charge pulses. At low voltages, the resolution of the detector depends upon the noise. The X-ray peaks are typically 2 to 10 electron volt wide. That is, it is the FWHM of the X-ray peaks. However, due to noise, this width can increase by at least an order of magnitude. The vacuum level should be maintained such that the condensation of molecules on crystal can be avoided. Pulse processor now. It is a charge sensitive preamplifier which is employed to convert the charge pulse to a voltage pulse. We next discuss about the analyzer. Multi-channel analyzer is used to sort pulses by voltage in the signals which are received by the analyzer. The energy of the X-ray can be obtained by measuring the voltage of the charge pulses. This energy is then sent for display and data processing. Here, data is displayed as histogram of intensity versus voltage. Let us discuss some features of EDS. First is the measurable elemental range. The measurable elemental range for EDS varies from B to approximately U. The measurement method is the energy dispersive method with the silicon or lithium semiconductor detector. The resolution of EDS is approximately 130 to 140 electron volt. The measuring speed is very fast. Multi-element simultaneous measurement is possible. Damage or contamination of specimen is little. The detection limit is between 1500 to 2000 ppm. Detectable X-rays per current are many. Let us now discuss about the qualitative analysis. X-rays generated EDS spectrum helps to carry out qualitative analysis to identify whatever elements are present in the sample when it is irradiated with high energy beam of electrons. There are three methods of examination. First one is the point analysis. That is, spectrum is obtained from a point which is radiated with electron probe. Second one is the line analysis. Here, the spectrum is obtained from a specified line which is displaying one-dimensional desired elemental distribution. Third one is the mapping. Here, the spectrum is obtained from a specified area displaying two-dimensional desired elemental distribution. It is often called as area analysis. Let us now study the X-ray mapping. It is used to study particular elemental distribution. For analysis purpose, electron beam is scanned over a particular area and the related characteristic X-rays are required. If the peak to background ratio is very low, then X-ray map does not show the distribution of desired elements. That is, it shows the distribution of continuous X-rays. Sometimes X-ray map may not show the distribution of elements which are not of interest because characteristics X-rays of elements of interest are close to those of not desired. It happens when energy difference between the desired element and the undesired element is equal to the spectrometer energy resolution. It takes more time to acquire one X-ray picture as intensities of X-rays are less in comparison to that of secondary and backscattered electrons. The resolution of X-ray mapping is limited by area analysis. Figure shows an example of X-ray mapping. The procedure, which quantitatively evaluates the points upon the sample gradually while scanning the electron beam, is called quantitative mapping. Precise elemental distributions can be acquired using quantitative analysis method even if peak to background ratio is low. It is a great advantage of this method. The other thing is the analysis area. Incident electrons, when strike the specimen surface, they get diffused and lose their energy by generating characteristic X-rays. This X-ray generation is spread over an area of around a few micrometers under standard operating conditions. Thus, a larger area needs to be analyzed in order to examine the particle of the order of few nanometer range in a SEM image. The analysis area can be decreased by reducing the accelerating voltage. However, accelerating voltage cannot be reduced below a certain level since the generation of X-rays requires high accelerating voltages. Another strategy to reduce the analysis area is by reducing the thickness of the sample under investigation. We next study the quantitative analysis. As characteristic X-rays intensities are proportional to the particular element's concentration, therefore quantitative analysis can be performed. The concentrations of unknown elements in a sample can be obtained by matching the intensities of characteristic X-rays of standard sample with that of the unknown sample. However, X-ray generated in the sample may be either absorbed within the sample or excite the X-rays from other elements before being emitted in vacuum. Therefore, correction is required in this analysis method for which the following requirements are prerequisite. First is it should have a flat specimen surface. Second is the electron probe should enter the sample in perpendicular direction. The third one is the distribution of elements in the X-ray generation area should be uniform. There are always some appreciable errors in this analysis method because some specimens do not meet these requirements. We next study the non-conductive specimen analysis. For non-conducting sample, metal coating is required in order to prevent the charging. But if requirement is to detect light element, then it is suggested to use thin coating film as heavy metal coating can block the X-ray emission through the sample because the X-ray intensities are less in comparison to secondary and backscattered electrons. Analyzing sample, with low incident accelerating voltage can cause some problems like first is the high excitation energy based characteristic X-rays cannot be detected. Secondly, quantitative analysis accuracy is degraded. Third, while performing the analysis or X-ray mapping, position shift in incident electron probe occurs. So, the suggestion for such problem is the low vacuum SEM can be used to analyze non-conducting samples because residual gas molecules present in the sample because residual gas molecules present in the sample chamber scatter the high energy electron beam, thereby increasing the analysis area. So students, let us now summarize what we have learned in this module. Firstly, the basic analysis principle of EDS was studied. Secondly, the principle of characteristic X-rays generation was discussed. Third, the instrumentation of EDAX along with the description of components was given. Fourth, methods of qualitative analysis of X-rays generated EDS spectrum was discussed. Finally, quantitative analysis was also described along with non-conductive specimen analysis. Thank you students for your attention.